Alright guys, I'd like to take a few minutes to walk you through some of the problems that you're supposed to be doing for homework tonight, just so you have a chance to kind of talk through them and listen to them. And I know this stuff is kind of new, so I just wanted to make sure that you guys were okay with it. So let's go ahead and look at these problems. Now before I do this, I do need to mention, since I am posting this online and I don't want to get in trouble and such, that these questions are all from Physics Lab Online, which was copyrighted by Catherine H. Caldwell. So these problems are her problems, and I am just working them for my class from school. So let's go ahead and look at these problems. So here's the first one. You've got two speakers that are in phase, so they're emitting the same sound at the same time, the exact same wave. The tone has a frequency of 85 Hertz and the speed of sound is 340 meters per second. The distance from one speaker to a detector distance is distance L, and the distance from the second speaker to the detector is distance L plus X. So we're going to be looking first for the first four values of X for which the detector receives constructive interference. Okay, so what I'm going to do first is I'm going to just go ahead and I'm going to take my 85 Hertz and my 340 meters per second and say that speed equals wavelength times frequency, which is 340 equals wavelength times 85, and divide, which when I do that I get 340 divided by 85, which is 4. Alright, so that's going to tell me right off that my wavelength is 4 meters. Now that's going to be important because when I look at constructive and destructive interference coming from different speakers, I'm looking at the superposition of the waves. And remember, the important thing when you have constructive interference is that the two waves, you're getting the same part of the wave at the same time. Remember, when you get a crest, you're getting a crest. When you're getting a trough, you're getting a trough. If you get somewhere in between, you're getting the same place in between. That's what allows you to have that constructive interference that has the really big change in amplitude, which then causes the louder sound. So what essentially needs to happen is when I have this distance from L from the speaker 1 to the person and then L plus X from speaker 2 to the person, what's important is not really the L. The L doesn't matter. It doesn't matter how far it is to the first speaker. What matters is when I travel that distance L, these two speakers are giving the same sound, right, at this point in time. So the important thing is, well, how far is X? How far does X need to be such that in that distance I get the same sound from the same wave, from the different waves? Okay, so one value of X obviously would be X equals 0. Right? Because if there was no X, if it was just length L and length L, that means that you would be hearing the same thing at the same time. Now, aside from that one, we can now look at several other possibilities. Okay? What needs to happen in that X to make sure that I hear the same thing from speaker 2 as I'm hearing from speaker 1? Well, during that X, I need to make sure that I'm going through a complete cycle. Right? It doesn't matter where you were at the end of L, because they're at the same place at the end of L. So as long as I go through a complete cycle between here and the listener, then I'm going to be getting constructive interference. And so if I go through one complete cycle, that would be a distance of 4 meters. And so it could be plus 4 meters or it could be minus 4 meters, because it could be 4 meters shorter as well. That would just take a cycle off. That would make this one cycle longer. Okay? Now, what else could happen during that time X? Well, I could go through two waves, right? I could go through two complete cycles. So if I go through two complete cycles, 1, 2, right, in a distance of 4 meters, that means that each cycle is going to have to be 2 meters long, right? And so, or sorry, they're 4 meters long, and so if I go through two cycles, each of which is 4 meters long, that means it's going to have to add up to 8 meters, right? So again, it could be plus or minus 8 meters, because as long as I'm adding or subtracting full wavelengths, then the difference is going to be a complete wavelength. Alright, so the next thing you should probably be able to figure out now is that I could change the distance. Now I'm changing the distance of my speaker, right? Each time I add in a larger distance to x, I'm either making it farther or closer. And so the next one would be, well, I could have 3 complete cycles. 1, 2, 3, each of which is 4 meters long, which means that would be plus or minus 12 meters. Okay, so there you go. There's the first 4, and hopefully that makes sense that you can use that idea to say, okay, I'm moving my speaker to make sure that this delta x is a specific distance, a difference between the L plus x and the L. Okay, the next question is find the first 4 values of x for which the detector receives destructive interference. Okay, so if we're looking at destructive interference now, we want to make sure that in that extra space we're getting a half of a wave, because I want to make sure that in that distance this wave is getting off by half of a cycle, which means each time I have a crest I'll have a trough. Each time I have a trough I'll have a crest, I'll get a trough. Every time I get a trough, I'll get a crest. And so that'll just make sure that everything's matching up exactly opposite. Okay? So that means in that time period, I need to have an extra or one less half cycle. So if I get a half cycle, okay, now the wavelength is still 4 meters. I can't change the size of a wave. So if the wavelength is 4 meters, and in that distance x I'm getting half of a cycle, how long is x? Well, x has to be 2 meters, right? Because I'm only getting half of a cycle, and a full cycle is 4 meters. So half of that is 2 meters. Okay, well, what else could happen? I could go through a complete cycle and then another half, right? Now again, that's in that distance x. What happened during L? I have absolutely no idea, nor do I care. Okay, so again, one complete cycle would be 4 plus another 2 for the half cycle, so that would be 6 meters. Okay, you can follow that procedure. You can go through 1, 2 complete cycles in another half, so that would be 4, 8, 9, 10. Okay, and you should be able to figure out the pattern by now. But again, what matters is what happens in this distance x. We can change that x based on how many cycles we want to fit into that distance. Okay, again, it could be x shorter, because that just means that now L is this one's going to be longer. Okay, so hopefully that kind of makes sense. Now let's look at a different problem. This is going to be very different because now the speakers can't move. Right? The speakers are now fixed. Go ahead and read the problem. Go ahead and pause it if you need to, and then I'll work through it. So again, this one's quite different because the speakers are fixed now, right? So if I go, if I'm going to use the same idea, right? Go 6 meters, right? So there's the L. But this time, I don't have an X. I know how far this is. This right here is 4 meters. Okay, so what I'm going to do now is it's asking for the frequencies that will allow the detector to get constructive interference. So now I'm going to be changing the frequency, or changing the wave itself, to make sure that it fits in that 4 meters. Alright, well, if I want constructive interference, what needs to happen in that extra 4 meters? Well, hopefully you answered that it needs to be a full cycle, one complete cycle. So what happens if I've got one complete cycle in 4 meters? Well, that means that my wavelength of this wave is 4 meters, which I'll use in a minute to get a frequency. Okay? Now, what else could happen in that 4 meters? Well, in that 4 meters you could have 2 complete cycles, right? And if you go through 2 complete cycles, then that means you're going to get constructive interference because you're ending in the same place as you start. Remember, what happens in that 6 meters doesn't matter, because here and here, it's at the same place. The sound, the wave is doing exactly the same thing. So I just have to make sure that during that 4 meters, it ends up where it started. And so again, I could go through 2 complete waves. Well, how long is the wavelength now? Well, I've got 2 complete waves in 4 meters. So if I take 4 meters and divide by 2 waves, that will give me a wavelength of 2 meters. Right? Okay. Well, what's the next possibility, right? It's asking for 4. Now again, I'm getting wavelengths first, so the next possibility, what else could happen in that 4 meters? Well, in that 4 meters, I could get 1, 2, 3 waves, right? So 3 waves in 4 meters. So 4 meters divided by 3 complete waves would give me 1.33 meters for each wave. All right? Now remember, this is still the wavelength. Okay? And remember again that this problem is different from the last one because this one I know this is 4 meters. And so I'm changing the wave. On the last one, I knew the size of the wave, and I was changing this distance, right? If you're getting confused, go ahead and look back at that one and remind yourself. All right, now the last one, 4 meters. So the last possibility is I could go through 1, 2, 3, 4 waves, right? And if there's 4 waves in 4 meters, that means that each one is 1 meter long. Alright, now that I've got these wavelengths, knowing that the speed of sound is 340, which is equal to the frequency times the wavelength, then I can just divide 340 by the wavelength to get the frequency. So, 340 divided by 4, 340 divided by 2, 340 divided by 1.33, so 85, 170, frequency equals 170 hertz, 255, so 256 hertz, and this one, of course, frequency equals 340 hertz, right? So there you go. There's the frequencies. Now the next one says, what are the first 4 frequencies that can be emitted which result in the detector receiving destructive interference? Now again, I'm only interested in this 4 meters here. The 6 meters before, this and this are the same, and so it doesn't matter what happened there. I could be in the middle of a wave, I could be at the beginning, at the end, I could be anywhere. It doesn't matter because I'm in the same place. And so what's going to happen during that 4 meters? Well, if I want destructive interference, then it's going to have to be half of a cycle off. So in that 4 meters, I could get half of a wave, right? If I go through half of a wave there, then that will mean that I'm half of a cycle off. So if I go through half a wave in 4 meters, that means the wavelength would have to be 8 meters, right? Because the wave would actually have to be 8 meters long in order to get half of a wave in 4 meters. Okay, next possibility, I could go through a wave and a half in that 4 meters. So if 4 meters is 1.5 waves, then 2.67 meters is the wavelength. Okay. Again, next one. In that 4 meters, I could go through 1, 2.5 waves, right? So if I take that 4 meters and divide it by 2.5 cycles, I get 1.6. So the wavelength could be 1.6 meters. Right? So hopefully you can kind of see the pattern that's occurring, right? Now I can go through 1, 2, 3.5 cycles. Right? Which should be 1.14 equals the wavelength, right? So again, all that needs to happen is that somewhere I go through an extra half a cycle, right? The whole cycles aren't going to affect anything because right here I'm at the same places at the beginning. Right here I'm at the same places at the beginning, which is at the same places here, which is at the same places there, right? So what needs to happen is just that extra half cycle somewhere. Now it's got to be in that extra 4 meters, right? Because this stuff for the 6 is going to match up with that stuff for that 6. Now again, once you know the wavelength, you can use wavelength to get the frequency. So 340 divided by the wavelength, so 42.5. 340 divided by 2.67. So we've got 42.5, 127. 127 hertz. 340 divided by 1.6, so 212.5, and 340 divided by 1.14, so there we go, 298. Okay. Hopefully that makes sense. Alright, let's go on and do one more. Okay, this one's a little bit different again. Again, looking at one slightly different idea. Okay, last one. Two loudspeakers are in phase and emitting the same tone. The speakers are 16 meters apart. The tone has a frequency of 85 hertz and the speed of sound is 340 meters per second. On the line drawn below the two sources, label the points where a detector would hear constructive interference, that is, loud sound. Okay, so this is going to kind of put everything together that we've been doing. Okay, again, I'm looking for a specific position. I know the frequency. The frequency is 85. We already found out before that the wavelength was 4 meters. Alright, so now what we're going to do, we're going to go ahead and do this mathematically. You could reason through it as well and pick out some points and kind of guess and check. But what I'm going to do is I'm going to do it mathematically. I'm going to do one or two solutions and then I'll let you find out the other points. Okay? So if I have some point at random and I say at that point, what is the distance from each of the speakers? Well, let's say that this is distance x from this speaker to the point. This distance then, if they're 16 meters apart, is going to be 16 minus x, right? Now, during that time x, right, so during whatever time x this is, they're going to go through the same process, right? We're going to be at the same point there and there. So what makes the difference is what is going to happen during this extra distance, right? The difference between 16 minus x and x. So if we say, okay, well, the first one was 16 minus x, and then if we subtract x, what do we want to get? Well, we want to get this difference. Now, what can this difference be? Well, it needs to be a complete number of wavelengths, right? If this is one wavelength, one complete cycle, then we're going to get constructive interference. So how long does that need to be? Well, one complete wave would be 4 meters. And so you can go 16 minus x, that's 16 minus 2x equals 4. Minus 16, la-di-da-di-da-di-da, and we get x equals 7. So x could be 7 meters, right? So we could then draw a point on here. I'll go ahead and change my color. Alright, so let's see, if this is the center, which is 8, then I can now, my color didn't change. Maybe that's it. No, maybe not. I don't know, my color's not changing. I don't know what to do. Anyway, so if that's 8 meters, then I want to make sure to put a point there at 7 meters, right? So 7 meters is the point, one of those. Okay? Now, what else is a possibility? Well, I could have that 16 minus x, and that could be equal to, well, what else could happen in this distance here? Well, I could get 2 waves, right? If I get 2 complete waves in the difference between these two areas, then it's going to be constructive interference. So I could do 8, right? So 16 minus 2x equals 8. Subtract the 16, negative 2x equals 8 divided by 2, negative 4, or negative 8, sorry, I was working ahead of myself, so x equals 4. So another one right here at 4 meters, right? So I'm going to get constructive interference there as well. Alright, now you can try this for 3, and then you can also do negatives as well. And you can probably find a couple more places where you're going to get constructive and destructive interference. Alright, so I invite you to go ahead and find a couple more places. You should find quite a few. Alright, so now let's look at the other one. Label the points where the detector would hear destructive interference. That's going to be the same idea, right? You're still finding the difference in those two lengths, but what else could the difference in those two lengths be? Well, for destructive interference, you want that distance to be half of a cycle, right? So 2 meters, right? So then we would have 16 minus 2x equals 2. Subtract the 16. Negative 2x equals negative 14 divided by negative 2. And we get x equals 7. That's because up here I subtracted wrong. Some of you have been probably been saying for the last 3 minutes, Mr. Bywater, 4 minus 16 is not 14. So let's go ahead and fix that. Negative 12, which means this should have been 6. I apologize. So that should be a 6. We'll fix that. I'll have to fix that someday. Oh well. Well, here we go. Next one, destructive interference was x equals 7. So that's where your destructive interference would be. Alright, so now let's do one more, just for good practice, and because I messed up one. So what else could that difference be? Well, it could be a cycle and a half. Well, one cycle is 4 meters, so 4 plus a half a cycle, that would be 6 meters. So the difference needs to be 6 meters. So 16 minus 2x equals 6. Subtract the 16, negative 2x equals negative 10, x equals 5 meters. So at 5 meters, I'm also going to get destructive interference. And I think you'll find that it's usually going to be between two of the constructive interferences, which makes sense because it should be together, off, together, off, together, off. Anyway, that's each of the questions. Hopefully that makes sense, and hopefully that'll be helpful in your homework tonight. See you later.